Hello and welcome to the second part of the economics on energy storage systems. And again this slide. So what we have learned in the last presentation, we already can deal with some aspects on energy storage related economic facts. So the annuities of our storage components can be calculated from the investment costs, from the interest rate, and from their lifetime. And this lifetime that might be directly given in a storage life in years, or indirectly we can calculate when they are given, for example, by their cycle life, the number of cycle they can do within their lifetime. And with that we can deal power related costs, the charger and discharger, energy related costs, and we also already consider here the lifetime of different storage systems. So, but now what do we need to consider? And we start at the end. So when we want to discharge a certain amount of energy, E this, and that can result of many different combinations of different powers with which we discharge a storage and a discharge time T this. The discharge power P this has a direct impact then on the annuity costs of the discharge technology. So the annuity A this NK is equal to A this 0, the investment in that technology, times the annuity factor of the discharge component. And that we can say is equal to A this specific 0, so the specific investment in that technology in euro per kilowatt, times the power for discharge P this times the annuity factor. That is what we end in, what we want to discharge. That means, but a discharge component, the discharge component of our storage system has a limited efficiency, so there are efficiency losses, and that means we need to store more than we later want to discharge. And therefore, before we discharge the storage, we need to have in the storage, when the eta this is the efficiency of the discharging technology, the energy this divided by eta discharge. And then we come to the storage process itself. Within the storage device itself, we need to consider two types of losses. And the first is we have efficiency losses of the storage itself. It's the eta store. And second, we have losses by self-discharge. So most storages have a self-discharge rate SD that we can give in percent per day, for example. And the latter one strongly depends on the time between charging and discharging our storage unit. And that means when we later want to discharge that E this, we need to consider all that losses. And when we charge the storage, we need to enter more. So the energy we need to charge to influence are itself the storage costs, is the annuity store NK, is then the initial investment into the storage capacity given in euro per kilowatt hour, times the storage capacity or the storage energy E store itself, multiplied by the annuity factor A store. And that amount of energy E store, that is E this divided by all those efficiency, the eta this, the eta store, and when we take into consideration the self-discharge, we multiply it also or divide it by 1 minus SD times T storage. And then of course when we initially charge the storage, we have losses in the charging technology. So there we have the eta char. And for some storage systems, charging and discharging technology, they can be identical, and for others they are different. So for example, when considering a battery energy storage systems, then the charging and discharging might be the same inverter. So the costs for that inverter is only once, but the losses we have during the charging and discharging process. So at the end, what we really at the beginning need to charge, when at the end we want to discharge E this, is E this divided by the eta this, by the eta char, by the eta store, and by the 1 minus SD times T store. And that charging energy again can be a result of many different combinations of charging powers and charging times. Often or sometimes the discharging power and the charging power might be the same, but it definitely must not be the case. So for example, we might charge the charging energy, E-charge, a very high power in a short time, but when we later discharge, we charge a small power over a long time. So there are many combinations we can think about, and they in some storage technology will influence the economics a lot. And what we should not forget at the beginning, when we charge our store, then we also need to pay for the energy that we charge there. So we need to consider the euro per kilowatt hours we pay for the charging process. And maybe later we get some refunds when we discharge the storage. Then we have a price for electricity or energy in euro per kilowatt hour discharge. What else do we need to consider? So far we have taken into account charging, storing, discharging. But sometimes things are more complex. And as an example, I would like here to discuss the matter of demand side management or demand response. Demand response is equivalent to a time shifting of electricity, for example, or any other form of energy. And then the consequence is the same effect to the electricity supply system than, for example, a storage device like a battery. But when we talk about demand response, there is no cost for charging equipment, there's no cost for discharging equipment, and there is no cost for the storage itself. For example, when you shift by make demand side manage with a refrigerator, you will not buy the refrigerator because you want to make demand response. You buy the refrigerator because you want to cool goods. So is there no cost at all? It's not the case. There is costs, and we need to invest in communication technology that tells when the compressor of the refrigerator should be in operation and when not, and we store the cold and discharge then this stored cold. And this communication infrastructure, that costs. And that communication infrastructure also is when we have battery systems, when we have a pumped hydro storage. But there we quite often neglect these costs because those communication costs is quite small, and when we put in relation to the storage capacities of a pumped hydro storage, we really can neglect it. But when we talk on demand response, demand side management, the communication costs is the only we have, and as quite often we only can shift small powers and small time shifts, small energies that can be differ then quite a lot in the economics of the energy storage. So we can head here, we should it make from a methodology point of view for all storages. So it's the ACOM NK is equal to the initial investment in the communication infrastructure times the annuity factor for the communication infrastructure. Although quite often it can be neglected. What else do we have? When it's coming to the coupling of different energy sectors, then things become more complex, and the simple scheme in the slides before need to be adopted. So just taking as an example power to heat. Finally, the thermal energy is discharged in the power to heat process. But we are doing power to heat because we need to shift electricity in time. And therefore, in cases like that, we need to decide case by case what we want or need to compare. Is it the electricity we charge or shift at the beginning, or is that what we discharge in the end? And finally, we need also to take into consideration, when we talk about the investment costs, that we have energy storage types where we cannot use all the capacity. So sometimes we talk of a so-called maximum depth of discharge, DOD, of a technology. And as a consequence of that, we need just to invest in more capacity than we in reality use. And with that overview, we should be able to calculate different economics of different energy storage solutions. And in the following of our course, we will deal with some examples to compare for different situations where we need storage, the economics of different storage alternatives. So thank you very much for your attention.